Hello, good morning everybody. Myself Shorapato from Mechanical Engineering Department of Future Institute of Engineering and Management. So let's start our presentation on our final year project, that is Machinability Investigation on Hardened Steel. So let's show the presentation. These are moreover the things that will be discussed in this presentation. Simply, machinability is a measure of each with which a work material can satisfactorily be machined. For example, there are two workpieces A and B under the same cutting condition and parameters, and if it is seen that during machining of A, tool's life is better, surface finish is better, less pore consumption happens, specific machining energy is less, then it will be said that A is more machinable than B. Now it is extremely difficult to optimize the above mentioned parameter at one time. It is like hit and trial experiment to find the correct combination. This project is a step toward that. We did some experiment by varying the parameters and condition so that all the parameters are optimized at a time. So we are going to make mathematical model and graphical representation using data we obtained or collected from past researches. Cutting speed, feed rate, depth of cut and machining time are identified as the process parameter which affect the various machinability aspect. It is evaluated by three characteristics, namely machining force in operation, surface roughness in workpiece and wear on cutting tools. Another important thing, because of COVID-19 outbreak and lockdown imposed by government, many of the experiments could not be completed, so it took help from past research data. In this slide, we can see there are a lot of factors affecting machinability which have been shown here, and all of them are important. But the ones which causes a drastic change are like basic material nature, brittle or ductile, mechanical properties of material, microstructure, cutting parameters and cutting condition like wet or dry condition, and tools geometry also. I would request my colleague Digvijay to take over from here. Thank you.
Hello, my name is Digvijay Bhattacharya from Future Institute of Engineering and Management, Mechanical Engineering Department. So, I would like to take over from where my colleague Shorapato left in this presentation. So, let's go to the slides and check out.
My friend Saurabh very rightly pointed out the important governing factors on machinability of any work material. Now, because our project is all about finding the best possible combinations of those parameters, it becomes really very important to know the possible ways of improving the machinability, because that will give us a correct direction for the experiments which we are going to perform or we have performed. Some of them are favorable changes in composition, microstructure and mechanical properties of the work material, proper selection of use of cutting tool material and geometry, and also optimum selection of parameters like cutting speed, feed rate, etc. based on tool work materials, and proper selection of the method of application of cutting fluid, because based on the cutting conditions, whether they are dry or wet, the machinability can differ a lot. And also proper selection and application of special techniques like dynamic machining, hot machining, cryogenic machining, which are basically economically viable and eco-friendly. They should be taken for improving the machinability. Now let's go on to the next slide. Now in this slide we can see the basic tests we have performed. We have summarized the tests we have done, and we are going to which we are going to discuss here, like roughness test, chip morphology test, power consumption test, and also three-dimensional cutting force test basically. And those three-dimensional forces are measured with the help of tool dynamometer. Let's go on to the next slide. Now let's see the results we obtained by analyzing the machining force with respect to all other parameters through the following graphs, where two parameters are variable and one is kept constant throughout these graphs. Now you can see this first graph. This graph shows the interaction effects of cutting speed versus feed rate, cutting speed versus depth of cut, and cutting speed versus machining time on machining force. Now, few important conclusions we can draw from this graph, which are you can check the points I'm going to tell with the graph. For a given value of feed rate, the machining force linearly decreases with an increase in speed, and if we increase the feed rate further, the force increases. Now, the probable reason for this might be with the increase of cutting speed, the shear angle increases, resulting in reduction of chip thickness and hence the machining force. Further, with the increase in feed rate, the contact area between the cutting tool and workpiece increases, and hence machining force increases. A similar behavior is observed on machining force due to the interaction effect of cutting speed and depth of cut. Now we see the variation of machining force with cutting speed at different values of machining time. Now you can see that it is found to be similar with the other natures, but it exhibits slightly non-linear behavior. So we can conclude by saying that the combination of low feed rate, low depth of cut and low machining time with high cutting speed is necessary for minimizing the machining force. Let's move on to the next slide. Here we can see the variations of feed rate versus depth of cut, feed rate versus machining time, and depth of cut versus machining time on machining force. So the conclusions we can draw from this graph is that the machining force increases non-linearly with feed rate for a given value of depth of cut. With further increase of depth of cut, the machining force also increases. Now it is observed that the combination of low feed rate with low depth of cut is beneficial for minimizing the force. Also, it is obvious, very obvious, that at slower feed rate there is a small resistance to cutting tool in the direction of feed rate. However, at large feed rate, the work material offers more resistance to tool in the cutting direction, and hence the friction increases, which in turn increases the machining force. Also, if we increase the depth of cut, the material removal rate increases, which contribute to increase in machining force. So I would like to conclude by saying that the figure clearly suggests that the machining force can be minimized by employing lower values of feed rate, depth of cut and machining time with higher cutting speed. Over to my colleague Krishnendu.
Hello, I am Deepanjan Chakraborty. I am from Mechanical, final year, FIEM. I am here to demonstrate a presentation on machinability investigation on hardened steel, and I will be continuing from the next topic where my friend Digvijay has ended up. So let's start with the analysis of surface roughness. Now, surface roughness plays a very important role in finding out the machinability index of any kind of operations. Okay, so let's go for it. Let's see the slides. Hello, I am Deepanjan Chakraborty. I am here to demonstrate a presentation on machinability investigation of hardened steel. I will be continuing from the next topic where my friend Digvijay has ended up. So let's have an analysis on impact of surface roughness, as surface roughness plays an important role in machinability. In all the three cases as shown in the graph in this slide, for feed, depth of cut and machining time, variations with respect to cutting speeds, the graph shows or maintains a linearity, that is a straight line, that enhances that with the increase in cutting speed, the surface roughness reduces. This is generally due to increase in temperature. If cutting speed increases, which ultimately makes the cutting zone soft and leads to reduction in surface roughness. With the increase in feed rate, the surface roughness increases respect to sensitive variations in depth of cut and machining time. In the next graph, we are seeing this. This is because with feed rate, thrust force increases, which leads to high vibration, conforms to heat generation, and surface roughness increases for this. Whereas in the last graph we can see the depth of cut at very lower values shows higher surface roughness because of rubbing and plowing action of chips, but roughness reduces with increase in depth of cut. But after a certain or medium, further increase in depth of cut leads to higher surface roughness. Therefore, combination of low feed rate, high cutting speed, lower machining time and medium depth of cut, especially 1 mm, in this case we have seen, is preferred for best finish. Now let's go to the next topic, that is the tool wear. It also keeps an important part in machinability index. Now let's come to the tool wear section. There also the three cases behave same linearity in an increasing manner for feed, depth of cut and machining time respectively. Almost all the graphs shows same behavior, that is, with increase in cutting speed, tool wear increases because abrasion of rake surfaces increases with cutting speed. In the next picture we can see that higher feed rate or depth of cut leads to tool wear because the contact between tool and workpiece increases due to this. Whenever the feed and depth of cut is high, the contact between the tool and workpiece is for a greater extent. So it is optimum that combination of cutting speed, feed rate, depth of cut and machining time is necessary in reducing tool wear so that we can use the tool for a perfect certain time and we can maintain a standard tool life for that. Thank you. That's all from my side. My friend Krishnendu will continue with the next slides. Thank you.
Hello, my name is Krishnendu Karmakar. I am the student of fourth year mechanical engineering of Future Institute of Engineering and Management. I am here to demonstrate a presentation on machining investigation of hardened steel. I will continue from the slide where my project mate Dipanjan ends. So we start with analysis of chips.
Through the experiments, we can observe generally short irregular chips are obtained in the lower cutting conditions where feed rate and both depth of cut both low. The probable reason may be rubbing and abrasive actions between workpiece and tool contact, whereas actual machining, where with increased feed rate loose arc chips are formed. We observed with increased speed continuous chips and with increased depth of cut long continuous chips are formed. The reason for formation of continuous chips are probably due to plastic deformation of work due to effective shearing for machining. If we go slide number 17, we can see different types of chips. First one is long loose arc type thin chips when cutting speed and depth of cut both is low. Second one is shorter loose arc chips when cutting speed is low to high. If we go third one is long continuous coil type chips when speed is increased from low to medium and depth of cut is increased low to high. If we go fourth one, we saw saw-toothed loose thick chips. It is formed at higher speed with higher depth of cut. Generally the chip breaking occurs at high speed. The next slides will be described by my friend Shayon. Thank you.
Hello, I am Sayon Saha, student of Mechanical Engineering 4th year. Now, I am going to discuss about the project outcome and the conclusion. So, let's start.
Now, here I am going to discuss about the important outcomes and the conclusion of the given project. We know that different cutting parameters like feed rate, depth of cut, machining force are all involved in the machinability of any product. Considering a constant feed rate as like 0.1 millimeter per revolution, we will see at a starting point the machining force is higher and the cutting speed is lower. As time increases and increasing the cutting speed will result in lower the machining force, which simultaneously gives a continuous chip formation and results in low tool wear. We also see that the machining force is very much sensitive to its feed rate. Now, increasing the feed rate from the previous one, taking the feed rate as 0.18 millimeter per revolution, we will see the machining force at the initial point is very much higher than the previous one. Now by decreasing the feed rate, depth of cut, machining time and by increasing the cutting speed will results in low tool wear, where in industrial work the cutting tool is a very important element for performing the machining operation. Low tool wear decreases the machining time, and side by side it increases the production rate of material and also helps to achieve the economical goals in the industry. Not only that, it also increases the better surface finish. Now, coming to conclusion, I can say that we have to keep in mind a positive approach before starting anything in this world. To accomplish our desired goals, we should design the plan in such a way so that everyone in the entire working field can grip the process layout very easily, which will increase the production rate in a very small time. That is, it will make or it will be profitable for the industry. We know that during the working time we have to face different obstacles, but facing obstacles is not an issue of an industry, but it is a gift, because the difficulties develops the working skills of manpower by resolving it, which in turn gives the better economical health of an industry and diversify the brand name. If we take some common example like General Electric, Rolls Royce, they made the aircraft turbine. If we take the pump company, that is water pump company, Texmaco, Crompton Graves, Bengal Engineering, all are well-known pump manufacturer company. So at the end, we can say that the resolving and facing difficulties will be better of the economical health and also increases the production rate for performing the same job in the next time, and also diversify the brand name of the product, because that is to everyone it is renowned as a production house of that specific product. In this way, we are ending our teamwork for the given project. Thank you.